Welcome. This week I was working on the three-tree theorem still, which tells that the abericity of a two-dimensional sphere is 3. So a sphere can also be described more axiomatically. It is a graph such that locally it looks Euclidean, meaning that the unit sphere is a smaller dimensional sphere, and that if you take one vertex away, it becomes contractible. And this forms a monoid using the join operation. So here we have a neat example. So the C10 is a one-dimensional sphere. So C4 is the smallest one, C4, C5, C6. These are all one-dimensional spheres, and the zero-dimensional sphere is the graph with 2 vertices and no edge. And if we take the join, we take the 2 graphs, the union of the 2 graphs, and we connect every node from here to every node here. This is the Zykov join defining the 50s, and this defines a monoid with the empty graph, the -1 dimensional sphere, as the 0 element. Also look at then primes in this monoid. Primes are graphs which cannot be decomposed in 2 different graphs. Well, both are non-zero. Now the nice thing is that every 2-dimensional sphere which is not prime must be one of these prisms. Prisms will play an important role here. Prisms are very special graphs. They have the property that the vertices with 4 neighbors form a closed loop. And whenever you have that, you have a closed loop, then you have automatically you can have no other choice than to have a prism. And so these are special in the sense that they are still abericity 3, but it doesn't come from a coloring. And we are using the 4-color theorem, which is a heavy theorem. We use that to upgrade it to a neat 4-color theorem. Before I describe this, let me tell you about the little shock I got this week. I was asking the Google assistant Bart about abericity, just to compare a little bit these 2 assistants, and Bart was telling me a lot of nonsense, like the cyclic graph has abericity 1, so lots of hallucinations, but it was also telling that every planar graph has abericity smaller or equal to 3. So these suckers know a lot of literature, so they have hundreds and thousands of books they read, and they kind of produce then a Markov chain on the set of sentences, and so you have then this generative AI, which is remarkably good. And so you can ask questions like, what is the abericity? And it tells you answers, gives you examples, and it was telling me that. And then I was looking again at the literature. I didn't find a proof yet in the literature, but exercise in Bondy-Morty, which uses some heavier results from other matter. Nash-Williams I've mentioned already, which characterizes abericity. So I kind of assumed that this is known, and actually kind of somehow also relieved. Of course, I was happy about this kind of result, this 3-tree theorem. It's a great result, but it's good to see that it already exists, and so I have kind of sniffed out the right theorem. The good news is it's not completely in vain what I did, because what happens is I have a little bit more information than just 3 trees. I get 3 trees which are special, and I call them neat forests. So the abericity 3 means you can cover the graph with 3 forests. So this is the graph, but then you can find disjoint forests which cover the entire graph, and that's equivalent that there are 3 in a connected graph, equivalent that there are 3 trees which cover the graph, or 3 spanning trees even. Now I have here kind of a little bit also definitions about trees. Trees are special because they are contractible triangle-free graphs. The individual trees can also be seeds, and then a forest consists of several components. So also these you can see algebraically, right? So trees are kind of the primes in this monoid, where the addition is now the disjoint union and not the join. The 3-tree theorem tells that for a 2-sphere, the abericity is exactly 3. And that implies, because every planar graph, that's a result of Whitney from the 30s, that every if you have a sphere, or K4, which is the tetrahedron, which is not a sphere according to this definition because it's contractible, but these two together make up the maximally four connected planar graphs. So you can, from that, you can take subgraphs of that, of a sphere, and you get planar graphs, and every planar graph essentially you can get that. This is the result then, which is known has abericity or smaller or equal to 3. Of course it can be smaller, like a tree itself is of course planar, and a tree itself has abericity 1. So, or a circular graph is planar and has abericity 2. But if you take a two-sphere, then the abericity cannot be smaller than 3, as we have seen. So the abericity of a sphere is exactly 3. That's the tree theorem. We have seen that it's bigger or equal to 3, and then 3 trees are enough, is that, follows from that. And the fact that two spheres are planar. So, but this is stronger. So the stronger statement is that every two-sphere can be covered by neat forests. A neat forest is a forest which hits every triangle. So what happens is when you do it with the coloring, so a graph coloring, a 4 coloring produces automatically a color on each edge, right? We have done that last time. We have the color C, which is when you have a 1-2 connection, or a 3-4 connection. B is 1-3 and G2-4, A is 2-3 or 1-4. So you can associate 3 colors. These are called Kempe chains. They're very famous because the work on the 4 color theorem heavily used that. And now, how do we prove that? So I'm actually happy that I did not see this exercise here in Bondi-Morti's book, because otherwise I would not have worked anymore, because it is known, right? If something is known, why should you work on it? And so I actually got, by not knowing, I got the stronger result, and the stronger result that you can actually cover a two-sphere or a planar graph by neat forests. And it's a little bit stronger, and it also tells that two spheres, this is a color theorem, kind of equivalent, that's completely equivalent just by going from the coloring of the vertices to the coloring of the edges, that all two spheres can be neatly 4-colored, which means that the Kempe chains do not form closed loops. So neatly coloring is not always possible, like in this case of the prism. It's when you take here the color, 1 and here the color 1, then you have to use the other 3 colors here. But then there have to be 2 different ones by the pigeonhole principle, which have the same color, and then you have a Kempe chain. Or they are colored. The second possibility is that they are colored with different colors, and then you have to use the 2 colors along the equator. You have to use the color 3-4 here, and then you have a Kempe chain, a closed Kempe loop here. So in any case, there is no neat coloring here. Fermat has used descent methods in number theory, and this is in topology. You can use descent methods and to get to a contradiction, but that doesn't work here, because what happens is when you are really small here, when you have a prism, then you have no more that situation that we can neatly color it. But the good news is, so what happens is you will eventually reach this prism, or you can contract it even more to get to a octahedron, the smallest sphere, then one before. So if you take an edge refinement here, that already allows neat coloring. Let me just show you how one proves this result. It's a kind of a new method, I think. It's a descent-ascent proof. So what we do is we deform the colored sphere. We don't deform just the sphere, we deform the colored sphere. So we have a 4 coloring, we heavily use the 4 color theorem. Every sphere comes also with a 4 coloring of the vertices. We take that for granted, and then we have a colored sphere, and what we do is we define a map which takes a colored sphere and gets us a smaller colored sphere. And this map is obtained by doing the obvious, right? By collapsing either these Heawood diamonds or larger ones, or Heawood kites. So this has to be, first of all, justified that you can do this, and also we have to worry about that this actually reduces the degrees, and you don't want to have a vertex degree 3, that's no more a sphere. But modulo this 4-color theorem, the proof of this theorem is constructive. So if we have the 4-color theorem given, if we have an oracle which gives us a 4-coloring of a planar graph, then we can construct a neat coloring. So what we are doing is we start with a colored sphere, we reduce its size and take the area as our Lyapunov function. So the area will decrease when we do something like that. It's kind of like a heat flow, rigid type flow. What we have to do, make sure, is that this is really working and compatible with the coloring. So what happens, for example, if you have here the same color here, then we can collapse. If this has not the same color, we cannot collapse like that. Also here, we need to make sure that if we have such a kite, this is a kite graph, we have to have the opposite vertices colored in the same way. That's not guaranteed by the 4-color theorem. Most of these kites are not these Heawood kites. We have to show that there exists a Heawood kite. I pointed out why this works. This only works because we have a closed Kempe loop. If we have a closed Kempe loop, we can guarantee that there is inside a leaf of the Kempe chain, and then near a leaf there is a Heawood kite. The vertex degrees of the neighbors is getting smaller, right? It's getting smaller by 2. So if you have a degree 4, that would be problematic. Before we do that, before we actually go to the Heawood kite collapses, we just collapse these diamonds so that we have less and less. If you have a closed loop, if you have a closed path of degree 4 vertices, these are all degree, maybe these are degree 4 vertices here, maybe this is no more degree 4. But if you have that, if you have a situation like that, so these are kind of, this is a whole path of degree 4 vertices. So this subgraph of all the degree 4 vertices always is a forest, and or has a simple closed loop. If it's a simple closed loop, it has to be the prism. You can just see constructively the only way how you can get there. You have to build a wheel graph on top and a wheel graph on the bottom. So the only way you get a closed loop in this subgraph of degree 4 vertices is that we have a prism. So in that case we cannot work. Once we reach the prism graph, then we just go one step back. One step back is actually either one step back has actually to come from from reverting one of these steps, and then you have a graph which you can show that it is just by construction that it has that it has a neat coloring, and neat coloring meaning a coloring so that the Kempe chains do not have loops. And once we have that, then we are going back. We have make this step evolution, make it smaller and smaller and smaller, and we can recolor it, and we are taking this new color, and we make the steps back. And if you make the steps back here, you can do that. So if you have a color here in the class of colored spheres, and you end up in the end with the same sphere than you have started with, but with a new coloring, and this new coloring is then a neat coloring. So it's an upgrade of the 4-color theorem. 4-color theorem can be made stronger by stating that the 3 Kempe chains are all forests, unless you are in a prism graph. The prism graphs are the only composite graphs in the space of 2-dimensional spheres. That's it for today. I'm actually wrapping this up and hope that over the weekend I have a draft which I can post.